All right, welcome to Bite Me, where we're squashing bugs one bite at a time. We are going to get into the rest of chapter 5. We haven't finished it fully, which is going to be our structs. Then we're going to get into enum and pattern matching. And hopefully we get to finish enums today. If we don't, I'll make another short episode uh, just going through the last bit of enums, and then we're going into packages and crates. So this is a good um oh, where am I? Oh, this is a good time for you to reflect on previous chapters. If you want to go back to a different live that we've done before, uh, and just refresh your memory, you can go ahead. I'm also putting out my Rust series, hopefully today, sometime today. Um, I have chapter 2 and chapter 3 projects done, and you can go through those chapters and try out those projects. Um, test your knowledge, regain all that knowledge that we just went through the last 2 weeks. All right, let me make myself smaller. Okay, so we went through most of the chapter 5. Now we're going to go into methods and structs. We did talk about methods before in previous chapters, maybe not in depth, but we've used methods in many different instances. So to understand what a method is, it's going to be that dot and then the method name, and then it's having parentheses at the end. So you'll know whenever I've said in previous lives that we're using a method. Okay. Methods are similar to functions. We declare them with the fn, the function keyword, and a name. They can have parameters and return value. They contain some code that run when the method is called from somewhere else. Unlike functions, methods are defined within the context of a struct, or an enum, or a trait object, which we cover in chapter 6 and chapter 18 respectively. Okay, I'm pretty sure we already went through method syntax before. Hopefully I'm correct, because I did not. I usually don't read these chapters before I go through them. Okay, unlike methods, blah blah blah. Okay, and their first parameter is always self, which represents the instance of the struct that the method is being called on. Okay, so I guess there are a couple different types of methods, and I was talking about a different type of method. This is the method I was referring to, the one down here. Dot area, and those parentheses, that's a method as well. But they're talking about this, IMPL. IMPL is also known as a method, and this one is strictly for struct, and I guess in the context of a struct. So if you see me say methods, we were talking about this method before, but now we're talking about this method. So sorry for the confusion. All right, so method syntax. Let's change the area function that has a rectangle instance as a parameter. Instead, make an area method defined on rectangle struct shown in listing 5-13. Okay, so we have a derived debug. Remember how we were using derived debug in the previous one, so that when it does print, or when we do a print line, it has a pretty, like, it has a specific structure when it's printed to the terminal. So it looks prettier, honestly. So, okay. So we have a derived debug above our struct, which is rectangle. Within our struct, we have width and height, which are both U32 bits. Now we have our IMPL, which is our method for our struct, and it's also called rectangle. Function is area, and then we are referencing self. Okay, and we're gonna get into why we're referencing self. We're turning a U32 integer, and then we're also going to reference self again with the dot notation, and then we're referencing with by indexing those specific parameters within those specific fields within the struct. Okay, so here we have self dot height. Then we have function main. We let rect1 bind to rectangle, which is our struct. We have width as 30, height as 50. Then we're print lining. The area of the rectangle is blank square pixels, and rect.area, which is this right here. So here we're multiplying height and width, and we know height and width are 30 and 50, which will be 1,500 or 1,500. So it should say, yep, the area of the rectangle is 1,500 square pixels. Okay, so define the function with the context of rectangle. We start an IMPL or implementation block, aka a method, for rectangle. Everything within this IMPL block will be associated with the rectangle type. Then we move to the area function with the IMPL curly brackets and change the first, and in this case only parameter to be self in the signature and everywhere within that body. In main, where we called the area function and passed rect1 as an argument, we can instead use a method syntax to call the area method on our rectangle instance. Okay, so it is, so I guess it's using method interchangeably. So it says over here, we can instead use a method syntax to call area. So this is how we use the method syntax. So it wasn't completely wrong, but we're using a specific syntax to call that method, I guess. This is also known as a method. The IMPL or implementation block, that would also be known as a method, and they are used interchangeably. I'm just letting you know. Okay, the method syntax goes after an instance, and we add a dot followed by the method name and parentheses and any arguments. In the signature of the area, we use a reference to self instead of rectangle reference to rectangle. The self, the reference to self, is actually short for self colon reference to big S or self. Within the implementation block, the type self is an alias for the type of the implementation block that the type IMPL block is for. Methods must have parameters named self on type self for the first parameter. So Rust lets you abbreviate this by only using the name self as the first parameter spot. Okay. Note that we still need to use the and or ampersand in front of the self shorthand to indicate that this method borrows self instance, just as we did in rectangle colon ampersand rectangle. Methods can take ownership of self, borrow self immutably, as we've done here, or borrow self mutably, just as we can do just as they can any other parameter. Okay. We can choose reference self here for the same reason we can choose reference rectangle in the function version. We don't want to take ownership, and we just want to read the data in the struct, not write to it. If we wanted to change the instance that we've called the method on as part of the method of what the method does, we'd use an ampersand mute self as the first parameter. Having a method that takes ownership of the instance by using just self as the first parameter is rare. This technique is usually used when method transforms self into something else, and you want to prevent the caller from using the original instance after the transformation. Okay. The main reason for using methods instead of functions, in addition to providing method syntax and not having to repeat this type self in every method signature, is for organization. We put all the things that we can do with an instance of the type in one implementation block, rather than making future users of our code search for capabilities of Rectangle in various places in the library we provide. Note that we can use a method that's the same name as one of the struct fields. For example, we can define the method on Rectangle that is also named with. Okay, here's our implementation block, Rectangle. Function is with. We are referencing self, and then we're going to return a boolean. Self.with is greater than 0 is our expression. So we're referencing self to this with. All right, and then our main function, we're going to be binding rect1 to rectangle, which is our struct, with the width of 30, height of 50. So this would be true. This expression would be true. So self.width, which is 30, is greater than 0, my bad. Now, if rect.width, we're calling this function right here, or this method. We're calling this function with method syntax, okay? And then we're print lining, rectangle has a non-zero width, and it is blank. And then we're also calling rect1 width. So I'm pretty sure it's going to, yeah, it's calling the width, which is 30. Yep. Okay. The rectangle has a non-zero width and it is 30. Perfect. I guess they use this implementation block to show us this expression that it is okay, that we can have a function that's also named one of the fields within the struct. Okay. Sometimes I get confused when I'm reading because it's just easier to break it down once you've already seen what's going on. You know what I mean? Sometimes it's good to go back. Here we're choosing to make the with method return true, okay, if the value of the instances with field is greater than 0, and false if the value of 0. If the value is 0, we can use a field within the method of the same name for any purpose. In main, when we follow rect.with with parentheses, Rust knows we mean the method with. When we don't use parentheses, Rust knows that the field with. What? Oh, okay. So it's rect1.with to know that they're talking about the field width, but when we use rect1.with with parentheses, they're calling this function. Okay. Pretty smart. Literally, these lives are just me trying to figure out what I'm reading. Honestly, for me, there's nobody in these chats. I'm the only one that's ever on these lives. So it's literally just me learning in real time. Okay. Okay. Often, but not always, when we give a method the same name as a field, we want it to only return the value in the field and do nothing else. Methods like this are called getters, and Rust does not implement them automatically for struct fields as some other languages do. Getters. Getters are useful because you can make the field private but the method public and thus enable read-only access to the field as part of the type public API. What? I did not know this. We will discuss this public and private. We'll discuss what public and private are and how to designate a field as a method as public or private in chapter 7. I did not know you could do that. Getters. I want to see what that looks like. What does it say? Return the value. Methods like this are called getters. Interesting. If you hear thunder and lightning, well, if you see any lightning in my eyes or whatever, it's literally because I do not have my glasses on. This is why I have poor eyesight, because I don't wear my glasses. It's because it's thundering outside and it's about to pour. So if you hear all of that, just disregard it. Right. Okay. Where's the return operator? Okay? In C and C++, two different operators are used for calling methods. Use the dot if you're calling a method on the object directly, and a return if you're calling the method on a pointer to the object and need to dereference the pointer first. In other words, if object is a pointer, then object is greater than something method is similar to, oh, I guess this is dereference. The dereference object within parentheses and then the something method. I don't get that. I don't understand that. Something I never really understand was dereferencing. So hopefully they really go into depth about dereferencing and things like that, because I am not very versed on dereferencing. Okay, Rust as an doesn't have an equivalent to the return operator. Instead, Rust has this feature called automatic referencing and dereferencing. Okay, calling methods is one of the few places in Rust with this behavior. Here's how it works. When you call a method with object.something method, Rust automatically adds ampersand, ampersand mute, or a dereference so that the object matches the signature of the method. In other words, the following are the same. p1.distance reference p2 method. Okay. Reference p1.distance p2 . I don't understand that. I really don't. The first one looks much cleaner. The automatic referencing behavior works because methods have clearer receiver to type of self. Given that the receiver and the name of the method, Rust can figure out definitively whether the method is reading ampersand self, mutating ampersand mute self, or consuming self. Okay, the fact that Rust makes borrowing implicit for method receivers is a big part of making ownership ergonomic in practice. So the methods are also dereferencing, automatic referencing and dereferencing. So, is it saying that we don't need to use a reference because we're utilizing a method and because it's automatically implemented in those things. There's a lot to think about right there. This is interesting because I don't even remember reading this the first time around. I literally forget everything after I read something, and I haven't read the rest of the book in forever. So these lives are literally me going back and looking at things that I thought I knew, but in reality I don't remember them. I don't. Okay, interesting. I don't know that. Methods are more parameters. Let's practice using methods by implementing a second method on the rectangle struct. This time you want an instance of rectangle to take another instance of rectangle and return true. If the second rectangle can fit completely within self the first rectangle, otherwise it should return false. That is, once we've defined the can hold method, we want to be able to write the program shown in listing 5-14. Okay, let's look at this. So we have a function main, we have let rect bind to this rectangle struct, and we have width, which is 30, height, which is 50. We have let rect2 bind to rectangle, which is another struct, and width is 10, height is 40. We have rect3, which is another struct. We have width 60 and width 45. Okay. So we're going to print line can rect hold rect2, and we're going to do rect1 dot can hold okay, we're doing a can hold method and print line rect1 hold rect3, and we're referencing rect2 and rect3 within that parameter or as an argument within our method. Okay. Now, the expected output would look like the following because both dimensions of rect2 are smaller than dimensions of rect1, but rect3 is wider than rect1. Okay, can rect1 hold rect2 is true, rect1 hold rect3 is false. So I guess I guess can hold method is a boolean. So if the second rectangle can fit complete within self, the first rectangle, otherwise it should return false. I'm trying to grasp what this can hold is really showing us because I'm not following. I don't think it's explained correctly. Okay, we know we want to define a method, so we will be within the implementation rectangle block. The method name will be can hold, and it will take an immutable borrow from another rectangle as parameter. We can tell what type of parameter we'll be looking by looking at the code that calls this method. rect1.canHold with a reference of rect2 passes in rect2, which is an immutable borrow to rect2, an instance of rectangle. Wait. rect1.canHold with a borrow or reference to rect2 passes in reference rect2, which is an immutable borrow to rect2. Oh, okay. I think I'm understanding. Let's keep reading. Okay, an instance of rectangle. This makes sense because we only need to read rect2 rather than write, which would mean we need a I can't read. We need a mutable borrow. We want main to retain ownership of rect2 so that we can use it again after calling the can hold method. So rect2 is a true mutable borrow. Is it mutable? No, it is immutable. It says we can only read rect2 because it's immutable. So we can only reference it once because immutable borrows can only be referenced. I am not understanding. Hold on. This makes sense because we only need to read rect2 rather than write, which would mean we need a mutable borrow. And we want main to retain ownership of rect2 so that we can use it after calling the can hold method. The return value of can_hold will be a boolean, and the implementation will check whether the width and the height of self are greater than the width and the height of the rectangle of the other respectively. Let's add the new can hold method to the implementation block. Why didn't they put this can hold above this one? Sometimes I don't understand people. Me literally reading this paragraph over and over and over again because I don't understand what's happening, and then they finally give me a block of code that tells me what's happening. Annoying. Okay, so this is function can hold. It has self referenced in it and other, which is referencing the triangle implementation block. Okay, returning a boolean. Okay, so that makes sense, true or false. And then we have self.width, and then greater than other.width, and self.height is greater than other.height. Okay, so our implementation block, we have function area, which is self, we're referencing self, and then we're returning a U32, which is width times height, okay? Now I'm going to go back here. So width times height, this would be 1500. This would be 400. My math skills are not sharp. I cannot do that one in my head. I'm bad. 60 times 45. Let me get the calculator out. Just because I know how to code doesn't mean I'm good at math. Okay, I think those two concepts get skewed. Because I'm actually very terrible at math. Okay, so 60 times 45 is 2700. Okay, so we got 2700. It is saying that self.width is greater than other.width. Now I want to know, where is other? What is other in this? Because we're referencing other and I'm not seeing it. I guess it's just, okay, so referencing the other, oh, this is an argument within it. So it's saying that it's going to be, other is the struct that is over here. So these structs are part of other. They should have just put this all together. I don't like how this is like separated. Okay, and then we're returning a boolean. Okay. When you run this code, I don't think it doesn't have any print line. Okay. When you run this code with the main function in listing 5-14, we get a desired output. Methods that can take multiple parameters, we use a signature after the self parameter, and those parameters will work just like parameters in functions. I don't like this explanation at all. I don't like how they explained it. It's actually extremely confusing once you put it together because they're in two different code blocks with an expected output that we didn't even know what can hold. We didn't know what this function did. And maybe this is just me shitting on the fact that I don't know how this, like, this area of the methods or whatever. But I thought this is extremely confusing, and I don't like how they explain this at all. Well, you don't like it. Right. So this can hold method, returning the boolean. Do we ever find out? That's what my question is. So what is this parameter? Rectangle, which is other, but then this is self. So what are we weighing these numbers against? Oh, I guess it's like this parameter or this field by other dot width, which is multiplying them. Okay, so like this would be 400, so is 10 greater than 400, and height, which is 40, 40 greater than 400. That just doesn't make any sense to me. And maybe it's because it's mathematics, but no, that doesn't make any sense to me. Sorry. Sorry. That made no sense to me, okay? That made zero sense, and it was extremely confusing for like no reason. Alright, associated functions. All functions defined within the implementation block are also called associated functions because they're associated with the type named after the implementation block. We can define associated functions that don't have self as their first parameter, and thus are not methods because they don't need the instance of the type to work with. We've already used one function like this. It's the string : from function that defined on the string type. Associated functions that aren't methods are often used for constructors that will return a new instance of the struct. These are often called new, but new isn't a special name and isn't built into the language. Okay, for example, we could use to provide an associated function named square that would have one dimension parameter and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. Okay, so our implementation block is rectangle with the function of square. Their size or parameter within this is going to be a U32. We're returning our big self. Then we have self, which is width size and height size. So the self keywords in the return type and in the body of the functions are aliases for the type that appears after the implementation keyword, which in this case is rectangle. Okay, to call the associated function, we use the : syntax with the struct name let sq equal rectangle : square 3 in this example. This function is namespaced by the struct, and the : syntax is used for both associated functions and namespace created by modules. I'm about to get AI on this because why is this not? I feel like this needs more explanation, especially when they're referencing self. it's a bit complicated because self is the rectangular block, right? But you're not seeing this syntax anywhere. Let SQ equal rectangle : square. So to call this associated function, okay, okay. So we're calling this one as an associated function because it's within it. Okay, I got upset. I got set too early, okay. I'm so sorry. That's my bad. I think it's because I got so confused on the last one. I was like, yo, ChatGPT needs to step in because I'm not understanding. I'm sad. Alright, cool. Okay. Multiple implementation blocks. Each struct is allowed to have multiple implementation blocks. For example, listing 5-15 is equivalent to the code shown in listing 5-16, which has a method of its own implementation block. So we have an implementation rectangle with a function area and we're referencing self and returning a U32. Then we have a width and height multiplied by each other. Then we have another implementation block called rectangle. Again, function can hold. We're referencing self and we're referencing other, which is going to return a boolean. Then we're using self.width greater than other.width and self.height is greater than other.height. There's no reason to separate these methods into multiple implementation blocks, but this is a valid syntax. We'll see case in which multiple implementation blocks are useful in Chapter 10, where we can discuss generic types and traits. Alright, so summary. Structs let you create custom types that are meaningful for your domain. By using structs, you can keep associated pieces of data connected to each other and name each piece to make your code clear. In implementation blocks, you can define functions that are associated with your type, and methods are a kind of associated function that let you specify the behavior that instances of your structs have. But structs aren't the only way that you can create custom types. Let's learn Rust enum feature. Okay, I do want to ask Claude a little question about self. So self is referencing, I guess we're referencing the self. We're referencing our own implementation blocks. Okay, so let me just write this down so I understand, and then I'll probably read what I have in the next video so that we're not taking up too much time in this video because we do have to go through enums. So let me just write down what I need. Alright, cool. Alright, enums and pattern matching. In this chapter, we're going to look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. First, we define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can either be something or nothing. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how the if-let construct is another convenient and concise idiom available to handle enums in your code. Okay, defining an enum. Where structs give you a way of grouping together related fields and data, like a rectangle with its width and height, Enums give you a way of saying a value is one of the possible sets of value. One is one of a possible set of values. For example, we might want to say that rectangle is one of, sorry, it's a bit dark in here. It's because it's raining. It's raining right now. For example, we might want to say that rectangle is one of a set of possible shapes that also includes circle and triangle. To do this, Rust allows us to encode these possibilities as an enum. Now let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, two major standards are using IP addresses, version 4 and version 6. Because these are the only possibilities in the IP address that a program will come across, we can enumerate all possible variants, which is where enumeration gets its name. Any IP address can either be a version 4 or a version 6 address, but not both at the same time. That property of IP addresses makes the enum data structure appropriate because an enum value can only be one of its variants. Both versions 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to these types of IP addresses. We can express this concept in code by defining the IP address kind enumeration and listing the possible kinds in IP address. An IP address can be in v4 and v6. These are the variants of the enum. So we have an enum, IP address kind, and we have v4 and v6. Now, IP address kind is now a custom data type that we can use elsewhere in our code. Isn't that cool? Okay, enum values. We can create instances of each of the two variants of the IP address kind like this. Let 4 equal IP address kind, : v4, let 6 IP address kind, : v6. So, nice. Okay. Note that the variants in the enum are namespaced under its identifier, and we can use a double colon to separate the two. These are useful because now both values, IP address kind 4 and 6, are of the same type. Now, I have the same type of IP address kind. We can then, for instance, define the function that takes any IP address kind. That would be function root, IP kind, and then IP address kind in curly brackets. And then we can call this function with either variant, which is root IP address kind, : v4 or v6. Now, enums has even more advantages. Thinking more about IP address type at the moment we don't have a way to store the actual IP address data. We only know what kind it is. Given that you've just learned about structs in chapter 5, you might be tempted to tackle this problem with structs as shown in listing 6-1. Now, so we have an enum, IP address kind, v4 and v6. We have a struct, which is IP address, and kind is IP address kind with an address, which is a string. Now we're going to let home equal IP address kind, which is our struct, and then we're going to have kind equal IP address kind enum v4 with the address and the string as 127.0.0.1. We have another one, which is a loopback, and we're equating it to the IP address kind struct, IP address struct with the kind field as IP address kind, which is our enum, as v6. Then our address is going to be a string, which is : 1, which is our loopback IP in v6, which is version 6. Here we defined a struct IP address, which has two fields, a kind field that is a type of IP address kind, the enum we previously defined, and an address field, which is a type string. We have two instances of the struct. The first is home, and then it has a value of IP address kind, which is v4 as its kind, and its associated address as 127.0.0.1. The second instance is a loopback. It has the other variant of IP address kind as its kind value, and then v6. v6 and has address of : 1 associated with it. We've used a struct to bundle the kind and address values together so that they have the same, so now the variant is associated with the value, okay? However, representing the same concept using an enum is more concise. Rather than an enum inside a struct, we can just put data directly into each enum variant. This definition of IP address enum says that both v4 and v6 variants will still have associated string values. Okay, so we're able to utilize this enum that we have as IP address with v4 and v6, and we're able to put it or associate it with strings. Then we bind home as the IP address of this enum. We're going to use this, I think this is, they don't call it fields, they call it something else. I'm just going to call it a field. Is it called a field? Oh, I think they're just called variants. Okay, so structs are fields, structs have fields, and enums have variants. So it's utilizing the first variant, which is v4, with the string : from as 127.0.0.1, and then this loopback variable, and it's going to use the IP address variant 6, v6, as a string from : 1. Okay, so instead of utilizing the enum and the struct, we're just utilizing our enum. That's it. That's all we need. We attach data to each variant of the enum directly, so there's no need for an extra struct. Here it's also easier to see another detail of how enums work. Do you hear that thunder? Crazy. Hopefully the stream does not lose connection. That would be awful. I'm just making sure that we're still streaming. Okay. Alright, cool. There's another advantage to using an enum rather than a struct. Each variant can have different types of amounts of associated data. Version 4 IPs will always have 4 numeric components. Will always have 4 numeric components and will have values between 0 and 225. If we wanted to store v4 addresses as 4 U8 values, but still express v6 addresses as 1 string value, we wouldn't be able to with the struct. So enums handle the case with ease. And we have another example of our enum handling this case. And you can see that v4 actually has 4 different types of input as a variant. And then we have v6, which is just someone's car alarm is going off. That's crazy. I hope we can make it through. What are we at? We're only at 6.1. I've been going slow today, my bad. So here we go. We have home is bound to IP address, which is v4. Then we have all of these different U8 numbers, which is going to be our all of these U8s. You see 127.0.0.1. And then we have our loopback address, and we're still using ::1 as a string. We've shown several different ways to define data structures to store version 4 and version 6 IP addresses. However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that the standard library has a definition we can use. Let's look at how the standard library defines IP address. It has the exact enum and variant that we've defined in use, but embeds the address data inside the variants in the form of two different structs, which are defined differently for each variant. Struct IPv4 address here, and then the struct IPv6 address. The enum IP address has both IPv4 address and IPv6 address, but we're inputting the variants. We're associating it with two other parameters, which is the struct IPv4 address and IPv6 address. You can see here. So this code illustrates that you can put the kind of data inside the enum variant, strings, numeric types, or structs, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition of IP address, we can still create and use our own definition without conflict because we haven't bought the standard library's definition into our scope. We'll talk more about bringing types into our scope in Chapter 7. Let's look at another example of the enum in listing 6-2, and this one has a wide variety of types embedded in its variants. So enum message, we have quit move, which has parameters or a struct which is inside of it, which is X I32 and Y I32 bit. We have write, which is a string, and then we have change color, which is 3 I32 bits. Okay, so this enum has 4 variants, okay, with different types. We have quit that has no data associated with it at all. We have move that has named fields like a struct does, write that includes a string, and color change that includes I32 values. Now define an enum with the variants such as one in listing 6-2 is similar to defining different kinds of struct definitions, except the enum doesn't use the struct keyword, and all the variants are grouped together under a message type. The following structs can hold the same data that the preceding enum variants hold. Right. Okay, so we have these structs. They're all kind of separated. Now, everything that the enum is holding, we have to utilize multiple structs to hold them because they're not in the same category. Now we have struct quit message, we have struct move message with both X and Y as I32s. We have write message, which is a string or tuple struct. And then we have another tuple struct, which is change color message with I32 values. Now, but if we use different structs, each of which has their own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6-2, which is a single type. There is one more similarity between enums and structs. Just as we're able to define methods on structs using IMPL, we're also able to define methods on enums. Here's a method called call, or named call, that we can define in our message enum. So we have an implementation block here named message. Our function is call, and we're referring to ourselves. Whatever would be in that method body, it's not there. Okay. Then we have let m equal message, : write, and then we have string from hello. We have m.call, so I think want to make sure it's not in the previous. Okay. Let M equal message, : write. So we're utilizing write in this enum. And this is how, so we're using the enum message using write, which is a string, and then we're passing this hello string as a argument within it, okay, in that variant. Then we're going to utilize this M, so m.call, and we're calling this function over here, which I'm not sure what would be in the middle of it, whatever is in it. It might print line something, if anything. Okay, so the body of the method would use self to get the value in which it called the method on. This example, we've created a variable m that has a value of message, : write string, which is hello, and that is what self would be in the body of the call method when m.call runs. Easy enough. So let's look at another enum with a standard library that is very common and useful option. So let's get into it. I'm just going to have a little snack. I got myself some grapes because I knew this episode was going to be pretty long. And we're definitely going to have to make another video. Let's just see how far we can get today. Because I'm definitely almost at an hour. I'm at 56 minutes. When you hear that, watch this live. Watch it. Just be disrupted by this rain. I'm scared. Alright. Let's get to it, okay? Option enum. This section explores a case study of option, which is another enum defined by a standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing. For example, if you request the first item in a non-empty list, you would get a value. If you request the first item in an empty list, you would get nothing. Expressing this concept in terms of the type system means that the compiler can check whether you've handled all cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Programming languages design is often thought of in terms of which features you include, but the features you exclude are important too. Oh my goodness. Rust doesn't have the null feature that many other languages have. Null is a value that means that there is no value there. In languages with null, variables can always be in one of two states, null or not null. In his 2009 representation, null references who? Whose 2009 representation? Okay. In his 2009 representation, null references the billion-dollar mistake Tony Hoare, okay, Hoare, sorry. The inventor of null had said this to say, okay, said this to say. I call it my billion-dollar mistake. At that time, I was designing my first comprehensive type system for references in object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put the null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, system crashes, which have probably caused billions of dollars of pain and damage in the last 40 years. Wow. So use null. The problem with null values is that if you try to use null value as a not null value, you get an error of some kind because the null or not null property is persuasive. It's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of the value being present or absent. The enum is an option T, and it is defined by the standard library as follows. Okay, so we have our enum, which is option, and I don't know what this is called. I guess these little thingies. I don't remember what they're called. Sorry. So we have none and some, and we actually are passing in a parameter within some, which is t. So the option t enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. Its variants are also included in the prelude. You can use some and none directly without the option : prefix. The option T enum is still a regular enum, and some T and none are still variants of the type option T. Interesting. So the T syntax is a feature of I'm gonna call them clips. Is that okay? What are those? I don't know what they're called. The T syntax is a feature of Rust that we haven't talked about. It's a generic type parameter, and we'll cover generics in more detail in chapter 10. Okay, I'll just call it generic T. For now, all you need to know is that generic T means that the sum variant of the option enum can hold one piece of data of any type, and that each concrete type that gets used in place of T makes the overall option T type a different type. Here are some examples of using option values to hold number types and char types. So here we got let some number equaling sum with an argument of 5 or a value of 5. Then we have let some char equal sum, which is an E character. And then we have let absent number equal option I32 equal none. Okay, so it's utilizing the option, but it says it's going to equal none, which is not sum. Now the type of sum number is an option I32, with the type of sum char as option char, which is a different type. Rust can infer that these types because we've specified a value inside the sum variant. Okay. For absent number, Rust requires us to annotate the overall option type. The compiler can't infer the type that the corresponding variant will hold by looking only at a none value. Here we tell Rust what we mean for absent number to be the type of option I32. So you can also type the variable. So some number and then colon I32 after. You can do that as well. So I understand like Rust is kind of, he already knows, the compiler already knows what we're trying to say, but it's best to type all of your variables. It's just good practice. When we have some value, we know that the value is present and the value is held with some. When we have none value, in some sense, it means the same thing as null. We don't have a valid value. So why is having option T better than having null? In short, because option T and T, where T can be any type, are different types. The compiler won't let us use an option T value as if we were definitely. What? Why was that difficult for my brain to comprehend? We were definitely a valid value. For example, this code won't compile because it's just trying to add an I8 to an option I8. So we have let x, and we have x as I8 equal 5. Then we let y option I8 equal sum, which is 5. Then we let sum equal x plus y. So see, they are typing right here. You see that? That's a type. So they're typing it, which is 5. Then we're letting y, which is option I8, I guess, which is the generic type. So it won't compile because we're trying to add I8 to the option T. Okay. I want to see what it was like over here. If we run this code, we get an error message like this. Cargo run, let sum equal x plus y, no implementation of I8 plus option I8. Is it because these were both options? And this is an option, and this is not an option? So it's saying that the following are other types: implement trait, add, blah, blah, blah. Don't know what it's trying to say. So intense. In fact, the error message means that Rust doesn't understand how to add an I8 in an option 8 because they're different types. When we have a value of the type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before we're using the value. Only that we have an option I8, or whatever type of value we're working with. Do we have to worry about possibly not having a value? And the compiler will make sure we handle that case before we're using the value. In other words, we can convert an option T to a T before you can perform T operations with it. Generally, this helps catch one of the most common issues using null, assuming that something isn't null when it actually is. Eliminating the risk of incorrectly assuming a not null value helps you be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. Interesting. The more you know. I didn't know null was such an issue until I read that passage. And you can tell that I'm more of a newer developer because I don't know all of these concepts of like in other languages as much. I've written in JavaScript before, but that is probably I've written in Python and JavaScript, but not at such a high level to the point where I'm making big projects on these things. All right. Where was I? Eliminating the risk of incorrectly assuming that not null values, blah, blah, blah. Safely assume that the value isn't null. Oh, okay. Did I read this paragraph? Eliminating the risk of incorrectly assuming a not null value helps you be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. Then you can use that value. You are required to explicitly handle the case when the value is null. Everywhere that the value has a type that isn't an option T, you can safely assume that the value isn't null. This can it was a deliberate design decision for Rust to limit null's persuasiveness and increase the safety of Rust code. So how do you get T value out of some variant when you have a value of type option T? So you can use that value. The option T enum has a large number of methods that are useful in the variety of situations. You can check them out in this documentation. Becoming familiar with methods in option T will be extremely useful in your journey with Rust. In general, in order to use option T value, you would want to have code that will handle each variant. You want some code that will run only when you have a some T value, and this code is allowed to use the inner T. You want some other code to run only if you have a none value, and that code doesn't have a T value available. The match expression is a control flow construct that does just this when used with enums. It will run different code depending on which variant of the enum it has, and that code can use the data inside the matching value. Let's see how long this is. We might be able to get through it. Let's see what I'm at. I'm at 1 hour and 11 minutes. I don't want to make this too long. Okay, I don't want to make this too long. I might just stop the video here, and we can make sure we're on 6.2. We'll do 6.2 and 6.3, and then we'll start chapter 7 fresh. So just make that. Alright, I hope you did enjoy this video. A lot of these lives I do enjoy doing, but no one's in my comments. No one's on my lives, it's just me. It's just me on my lives. So, hope that you also keep following along to my next live. I have to edit actually. I have to edit some of the new edited videos for my Rust series. Go and check that out and try those projects. I think it's going to be a little bit of a good refresher if you are following along on these lives. Yeah, I'm glad that we get to do this together and learn together. And a lot of times on these lives, I don't know what I'm talking about, and I'm reading it and learning it just at the same pace as you are. So I think it's fun that we're learning together. All right, I think that's the end of the video. I'll see you later.